I have an unavoidable appointment at 11 to 11:30. So I need to start class next Tuesday at 11:35. Now, ideally, I would go till, say, 12:45 to try and catch up a little bit. Who couldn't stay till, say, 12:45 or 12:50? How iffy is that?
It would be inconvenient, but it would cost me a different class that I would stay here.
So let's not push it too far. How about knocking off a few minutes? Okay. Okay, I think those are the announcements. Back to where we were. We had defined the vacuum persistence amplitude, and we had seen that in perturbation theory I could write it as in perturbation theory in the source, but non-perturbatively in the real interactions, I could write it as in the obvious notation, J1 to Jn. And in the obvious notation, phi1, phi n. Okay. And I think I was being silly. This is, of course, a functional Taylor series. And in fact, all our perturbative expansions are Taylor series, okay, in whatever you're perturbing in. They may not be convergent Taylor series, as is the case in when we're perturbing in the coupling, but they are Taylor series. This is a Taylor series. It's a functional Taylor series in J. Because J is not it's not a number, it's a function. It's not a regular Taylor series, it's a functional Taylor series. Okay? We're expanding in, again, I can do a function which is a function of x1, x2, x3, and I could Taylor expand, powers of x1 to the 7th, x2 to the 3, x3 to the 14, 3.5 plus. That's a Taylor series in a vector. This is a Taylor series in the vector x. We can think of this J as being a vector whose components, this is a Taylor series in xi, this is a Taylor series in j sub x, where the index is continuous. So it's a pretty big vector. In fact, it's a functional function, and hence we say it's a functional Taylor series. Okay. And that's why this thing is called the generating, or one of our, this is the first one we've come to, but it's a generating functional. And that's because every dynamical question we've ever been taught to care about is sitting inside here. And in fact, it's sitting as a kind of Taylor coefficient. So that you can in fact re-express all of these things as so if somebody would only hand you this functional, it's a functional because it depends on J, and J is a function. If somebody would just give this to you by just getting the various Taylor coefficients, you would have this. And you could then set J to 0 and just talk about the theory without sources. This would still be a very interesting function in a theory without sources because it does have regular lambda 5/4 interactions, right? This is the thing we care about. At the moment, I've just written it non-perturbatively, but I could further expand this perturbatively in lambda. But that's not what I'm pointing to. The entire answer for the endpoint function, even if I didn't care about sources, I could get it by being given the vacuum persistence amplitude in the presence of the source term. By just taking the Taylor coefficient, I could take the Taylor coefficient and here. Just take the Taylor coefficient and set the source to 0. Okay? So it's exactly like you want to pick out the third term in a Taylor series, differentiate 3 times the function, set x to 0, you're expanding in x, Taylor expanding in x, and that'll actually be the coefficient, which of course is x independent, because it's the coefficient of the powers of x. Okay, so that's the structure of this thing. And so then I had defined this to be e to the I, yet another functional w of j, which is the generating functional of a planed connected so this is the generating functional for all correlators. But if I was being very careful, I would want to say non. Well, actually, this is just the entire thing. You can decide to throw away the back graphs. But this thing is generating functional. No, sorry. This is the generating function of all connected correlators, but that requires proof, right? Why is it that the log of all correlators are the connected correlators? And so
Sorry, what do you mean by non-vacuum correlators? It says
sorry, what I mean is the ones where you throw away the vacuum zone. Discarding vacuum bubbles, just as an example. This times this is an interesting Feynman graph. Tells you to throw those away. If you've forgotten why we throw these away, look in, I think somewhere in the first 5 chapters, it's a part of it. Hopefully the stuff you found for the classroom. Okay, so let's just focus on the kth power of W. And ask, what is the typical kind of diagram that's sitting in the kth power of W? Okay. So I'm just going to assume, I'm going to start by saying I insist that W is the connected diagrams, are the connected diagrams. Okay? Then my job, to make this clear, is to show you that the exponential of all the connected diagrams are in fact, all the connected correlators are all the correlators. Okay. And so this, I hope it goes without saying, we can further expand in lambda. So, see, by talking about this, I'm talking about all orders in perturbation theory that would contribute to this. Or if you're really strong non-perturbatively, here's the endpoint correlator. But you can think of this as the sum of all diagrams with, 1, 2, 3, 4, n. And you're drawing all possible diagrams that could contribute to this, maybe even so the sum over all these things would be just one of these things. As long as I fix 1, 2, 3, 4 up to n as these points 1 to n, then any diagram would contribute to this, whereas only, and so what I mean is perturbatively there's a non-perturbative meaning. So it sounds like the word connected necessarily means, well, show me a Feynman diagram. This is connected, but I'm saying it's connected because it has lambdas there. And I'm doing perturbation theory, and you can see that it's connected as a diagram. Even non-perturbatively, the word connected means something, although it's just easiest to take a glance at a diagram and say, hey, that's connected, and that one is not, that product is not connected. But non-perturbatively, it is also, so for a statistician or a probabilist, connected diagrams, connected correlators mean something, and they don't know beans about art. Yeah.
Wait, so is the one on the right no vertex, just crossing?
No, sorry, there's a lambda there.
Okay.
And I'm multiplying these two. So this is a 4 to 4 process.
Oh, but the two aren't connected.
But they're not connected, right? Yeah. And so in general, if you're doing statistical correlators, and you have phi 1 to phi 4, and then say phi 5 to phi 8, you're calculating such a correlator. And what you're calculating is, if you're finding a contribution where what you're really saying is, yeah, these things are correlated, these 8 variables are correlated, but in a funny way. These 4 are correlated, these 4 are correlated, but the two sets have nothing to do with each other. Then that's an example of a disconnected correlator. That means that all the hard work is figuring out how these 4 variables are correlated and how these 4 variables are correlated. And then if somebody asked you for this correlation, it was obvious, okay? Because you know the distribution here and here, multiplying the two is trivial, okay? That is, you might as well just do that. So, in statistics, in the sense of correlations, you're obviously wasting time by calculating correlators when you know that only some subsets of variables are correlated. You should really work in terms of the subset. That's exactly the utility of connected diagrams. Again, it's obvious that connected diagrams make life easier, or rather, they're the hardest bits. You calculate this connected diagram, and said, no, I insist that we, have this diagram. This is where everything is, all these phi's at all these points are correlated in an intractable way, okay? I can't factorize. So that's the virtue, non-perturbatively, of the notion of connected correlator. And, but if you want, if that's not familiar to you, just think in terms of the diagrams. These are the diagrams where the diagram, when thought of as a perturbative expansion and coupling, looks connected, okay? So let's focus on this and just see why it is that, as I said, this is something not about field theory, this is just something about, if you like, statistical correlation. Why it is that the exponential of the connected correlators are all correlators. And so you can just look at a typical term. Would be something like, so let's take each of these k factors of W and look at some diagram that would have been there. Let's say we were calculating a 4-point function, okay? So we might have had this, 1, 2, 3, 4. There might be another factor where it's this. Whatever I write better be at least a connected diagram. There might be no, I'm doing a bad job. Hang on. No, let's take any diagram. I'm not going to insist that it's a 4-point function. Then you can see what happens. The magic happens between different numbers of points. So here is a diagram that might have been inside the first factor. So I'll put dot 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 plus. Okay, and then dot 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 plus for sitting inside the third factor of W is just this 2-point function. And then maybe on the 27th factor, by pure chance, I have the same thing as the first factor. Okay, and then okay, so here's the kth factor. Here's the first factor. Actually, in every factor, I've written all of W. It's just that there it is. See everything, but I've just focused your eye on one particular term. But everything at the moment, there's no approximation. This is literally equal to this in the sense that you're supposed to imagine all connected diagrams, all connected diagrams, all connected diagrams, all connected diagrams. Except that in each case, I'm just telling you to zoom in and look on one particular term. Yeah.
Since Wj is not being expanded perturbatively in lambda, shouldn't the first and second terms?
No, I'm saying take Wj.
Yeah.
Imagine expanding it both in J and in lambda. Okay. As I said, if I were going to do it slightly more slickly, the expansion in lambda would not be necessary. However, then the proof would proceed a little more algebraically and a little less diagrammatically. So I'd rather just go with the diagrammatic one because you'll see it. You'll see the point like that. So do imagine that This thing, of course, there's J's here that are being integrated. You know that part. So we are expanding in J. But furthermore, let's imagine the entire perturbative expansion till whatever order in perturbation theory you feel like stopping. Okay? The proof that this is non-perturbative, and those who feel ultra sophisticated can go and, as an exercise, show that this is true non-perturbatively. But in this class, you're only guaranteed a perturbative education. So let's just do that. So, of course, there's a gazillion terms in this factor. There's a gazillion terms in this factor and here and here. And so if I have to write this whole thing out, I have to take like one diagram from here, one from here, one from here, one from here, one from here, and that's one contribution to that. So that's why I've explicitly drawn one. Okay, just to show you what's about to happen. So if we just take this one contribution to W to the K of this times this times this times this times this, okay, then that would clearly be, so this product, I won't keep writing these little source things. This is all multiplication, right? This is clearly a contribution to this. Except the combinatorics. That's all that this exercise is about. Just what does that k factorial mean and so on. Okay. But clearly, if you take connected diagrams and you multiply them together, then of course it is some disconnected diagram. There's no question about that. That's what I've indicated here. And furthermore, if you take any diagram which is disconnected, or the most general thing that you could take, a diagram here, either it is connected by chance, in which case it will come out of the term the k equals 1 term. Okay, k equals 1 terms are just all the connected diagrams themselves. So if I just take a random diagram out of this, and it happens to be connected, then I know where I'm going to find it. I'm going to find it in the k equals 1 term. If in fact it contains k disconnected pieces, a random term here, then I'm certainly going to find it somewhere. I mean, it's going to have this kind of form. And so our only question in saying that they're actually equal is whether all the coefficients are matching up. Certainly the structure here is there, and any structure that you can think of there is something that would come out of expanding this, and we're just worried about the factor. And so that's why I've drawn a number of sort of different looking pieces, like these guys. Say that this is a term in which that everything except this fish diagram, silver fish diagram, whatever. Anyway, everything except this fish diagram is, say, done once. It appears only once in this string. So there's no more copies of this in this string. Then, you see, we have this k factorial sitting here. But indeed, I could have got this guy from this last term, or I could have got it, in other words, I could have got this one from here and this one from here, or the other way around, and it would have been the same thing. Okay. So in this example where two of them happen to be the same but the rest are different, there will be a combinatoric factor. I mean, the contributions to things that look like this, since the product structure, you don't care about what order you're multiplying. You'll get k factorial, but you'll also get k minus 2 factorial here. So if I just take the two identical guys out of the picture, and I permute all the other guys exactly in all possible ways, they'll all give me contributions that look like this. And permuting those k minus 2 remaining guys would be to say k minus 2 factorial. Okay. And whereas for these guys that were exactly the same, there was only, if I have to take them out of these two boxes, I have to get this guy, I have to get this, I mean, there's no switching, okay, so there's nothing like that. And, but then on top of that, there's one other class of ways where I could have got exactly this expression. The place where I took the two identical guys out of, I could have taken these two silverfish diagrams from any two of these places. Let me see if I can get that right. What's that? How many ways could I have got the silverfish? So that's k times k minus 1, right?
Yeah.
Darn it.
Now they all just cancel.
They all canceled. However, we know that there was so what you know off the top is you know your symmetry factors. And your symmetry factors would have said, look, these two were at least interchangeable components. And so I should have had a 1 over 2 factorial symmetry factor.
You can get it if you say, out of k you choose 2.
Yes.
And then all other things are factorial, meaning k minus 2 factorial.
Yes.
So k choose 2 times k minus 2 factorial gives exactly 1 over 2 factorial. Which you
Wait a second. Didn't I just do that? From k choose 2. K choose 2.
Yes, exactly. Yeah.
Then here's my k minus 2 factorial.
K choose 2, you forget the 2 factorial in the...
Oh,
Yeah.
That's
Yes.
very good.
Yeah.
So this thing is canceling this, and this is the expected, not expected meaning the when I say from omega, omega, j, I just mean the regular way of drawing diagrams. It's just the sum of all diagrams, right? So anyway, that was one example. Now the thing is to see that in general, any set of diagrams I write down, I could have permuted everything possible, and I would end up getting k factorial on top. Okay, so should I write that somewhere? Okay, I'm not sure whether I need that. We're done with this, right? Class half an hour late Tuesday. Anybody who came in late. Look for homework 2 by the weekend. And homework 1 in. Yeah. So, in general, K connected diagrams product of k connected diagrams can be chosen from W to the k in k factorial ways if identical sets of exact that identical subsets of give me another number k l If I have L identical silverfish, I've been taking the count as just being k factorial in the dumb way. Of course, what I want to say is you get a 1 over L factorial. Do I need to belabor this? No, you guys think about it. So, except that identical subsets connected diagrams have extra 1 over L reduce this count by 1 over L factorial. Which is just obvious then. It's just saying that in this way of saying k factorial, I could have got these diagrams in any possible permutation. When they're identical, even if there were L of these guys that were identical, there's no sort of permutation that acts on those. There's only one way of pulling out a silverfish from those L places. That's it. That means you overcounted here by L factorial. That's what this 2 is an example of. And so, therefore, this disconnected diagrams. It's a sum over all sorts of products of k disconnected diagrams with divided by product of L I factorial for each subset I of Li identical connected factors. And this corresponds precisely to the symmetry factors in okay. That's not to say that there aren't other symmetry factors. Even a connected diagram by itself may have internal symmetries that give rise to symmetry factors and calculating it. But we are only trying to understand the extra symmetry factors that come from a disconnected nature of the diagram. Okay? So whatever symmetry factors you're used to doing for a connected diagram, you keep doing it. But on top of that, there are symmetry factors just from the fact that this disconnected component and that happen to be the same. And so that's where you throw it in. Okay, so in a sense, if we could just work out the connected generating functional, life would be good. And even non-perturbatively, I could just say, give me this, I'll just take its exponential and I would have this already. There's no more, it's sort of a waste of time to calculate all these diagrams when you can get them all from that. Very good. This is the object, W, or if you want, omega. W is very important for, you might say, I don't care at the moment, I can just think about this, since I'm not actually going to compute all diagrams. Why not just think about this? Later on, it's going to be very important to think about W. But either of these objects, which is to say all diagrams put into one big heap and thought of as the Taylor expansion with respect to the sources of the vacuum persistence amplitude, this is what we want to compute. And the next move we're going to make is the path integral formulation of quantum mechanics and quantum field theory in order to take maximal advantage of this way of doing things. And also we'll see it's a kind of the high-tech way in which we can do perturbative diagrammatics for renormalization, and even then for gauge theory. Okay. And certainly the great virtue of path integrals is they keep manifest relativity. Okay. So the next topic here, so you're supposed to keep this question in your mind. This is what we want. But now we're switching topics, if you want, moving to something else, namely path integrals, and then we'll formulate how to calculate this using path integrals. Okay, keep that target in mind. So we're switching to path integrals in quantum mechanics. And sometimes they're called path integrals because they, as you see, are summing over paths in quantum mechanics, but they are often called functional integrals because they're summing over fields, which happen to be functions of space-time. They're called functional integrals in quantum field theory. In fact, I'm going from one to the other. Okay? And in this thing, one of the great virtues is manifest relativity. And a simple classical limit. And it turns out the simple classical limit aspect of functional integrals or path integrals not only is it insightful in terms of just the literal classical limit, but the idea of, but it will be very important in an odd way. It will be very important in proving or setting up how you were to do renormalization to all orders in perturbation theory till you get tired. Okay. This idea of what are the classical looking pieces of a quantum calculation becomes the key technical step in sort of iteratively renormalizing perturbation theory. Okay, so it's very important for both of these reasons, and for gauge theory. So this is why we're learning all of these. That's the value added of this. There's one thing that's less manifest. So compared with just writing down a Hamiltonian, which is Hermitian, and hence time evolution is unitary. Compared with Hamiltonian methods, we lose manifest unitarity. Okay, so there's a give and take. And that's why you're being taught both, if you like, canonical quantization and Hamiltonian and all of that stuff, and path integrals. Because each has regimes and things that you could study where what you care about is more manifest in one way of thinking or the other. And in fact, they are your two eyes. So you really want to understand a problem, you would ideally like to see it from both methods. Many people, once they see the path integral, are so disenchanted with the Hamiltonian and the non-relativist, the non-manifest relativity of this approach, that they say, why couldn't I have been taught path integrals right from the start? And indeed, I think there are attempts to try and do that in various books. And I don't know the final balance sheet, but I think you are a bit lost if you only have one of these up your sleeve. So why not have them both? I find in real research, and I think even in learning the subject, that having both is crucial. So when you see this and it looks very beautiful, don't forget all this. Okay. Functional interval. Anything else I want to say? As I said, the most obvious sense of the classical limit is you think again of Feynman's paths, which we're about to do, in case you've never seen it, but summing over from some particular x to some particular x prime as a function of time, and you're summing over these paths. And that's giving the amplitude to go from here to here. And of course, there's a classical limit called the classical path, whatever that is. And there's some sort of a limit in which the summing over paths turns into just taking one special singular path called the classical path. And that's obviously one of the reasons that Feynman and his, I guess, predecessors all the way to Huygens or whatever were thinking this way. Okay, so there's some great utility and great physical insight in doing things this way, but it does hide a little bit as well. Okay, so let's start with that motivation. So let's do one-dimensional quantum mechanics, where you have a Hamiltonian, which is p squared over 2m plus v plus some potential. Now, I wanted to keep track of the fact that these are operators. I'm doing quantum mechanics. And in the course of doing path integrals, things will switch from being operators to being C numbers, and I want a notation that makes it completely clear whether something is an operator at any stage of the development or whether it is not. I want to hijack this symbol, which I was using to represent Heisenberg operator. I'm trying to see whether I can get away with it without causing confusion. Because at some other point, there are Heisenberg operators too. This is just the, so here it is. I'll just put the S there. This doesn't. So here, I just mean operator C number but still Schrodinger picture. Schrodinger operator. Okay,
What
so
does the one-dimensional refer to?
the one dimension refers to the fact that this x is there's only one x.
Okay, so it's not like a space-time dimension. It's like your.
Yes, that's right. I'm actually doing quantum mechanics, non-relativistic, in exactly the notation that you learned as undergrads and so on and so on. But this, okay. We'll see how we can get back to field theory a little more. in fact, so the question, the dynamical question, is if I start at x initial, then what is the amplitude to x end up at x final after some amount of time? And the answer is e to the minus I h hat okay. So we just want to know, start at x initial at time t initial, you evolve till time t final, and you ask, where are you likely to be? And this is the amplitude that we're asking about. So this is the baseline question in non-relativistic quantum mechanics. Okay. Sorry, so maybe I should have said non-relativistic quantum mechanics of a single particle. There's no field theory, there's no multi-particle anything, it's just a single particle. So that's why I can just label the state by where it is, because there's only one of those particles. Right? So okay, so this is the baseline question. In fact, our question that we need is just slightly, so in fact, want v of x hat I want time-dependent potentials. As non-relativistic quantum mechanics, you have all studied time-dependent potentials, which are really modeling, not that the laws of physics are time-dependent, they're modeling some other aspect of your system, which is not the one particle that you're studying, like your experimental apparatus or some electric field or whatever, and you're treating it as an outside force, and you control it as an experimentalist, and it's time-dependent, and that's the situation. I haven't done that here. That's in fact, this is in fact what I want. I want to consider this general situation where the Hamiltonian is time-dependent explicitly in this sense. But our derivation will straightforwardly, meaning you could do it, forwardly generalize for, now, so why don't I just do it? Well, only because here I can just write the evolution operator as this, whereas in fact, the general question would have been this, e to the minus I, sorry, time ordered, e to the minus I integral dt prime h hat of t prime. H hat now depends on t prime because the potential depends on time. And then I go from ti to tf. And I just don't want to keep writing that out. But everything I'm about to do as an exercise, you can just sort of think it out for this case. Which again has the simple interpretation. I start at xi, I time evolve, and if you recall, this is the time evolution operator. And then I end up at xf. And the only thing that's got the time ordering here is because the Hamiltonian at different instants does not commute with itself. Because the Hamiltonian at different times is not the same thing. And so in general, operators don't commute, and this is certainly an operator. So you can watch that for yourself, maybe even do it in your head as I'm just writing this out. Note that there's no hat here, just to get the notation right, there's no hat here, there's no hat here, because I'm just asking. 5 yards to the right, 7 yards to the left, what's the amplitude? Okay, so that's it. Okay, so a number of you, maybe all of you, have seen this before, but let's go through it, because it's so relaxing to do. And and then look for all the subtleties that come up in the field theory case. Okay, so this XF many of you know, the idea is that we subdivide, it's very much like the proof I used of that, what I call the general formula of perturbation theory. Time evolution is broken up into small, small steps. And that's what I'm about to do here. So I write my XF like so, and then I should leave myself some space. Then so I'm going to call this thing delta t. Again, it makes my life easier, but you can do this more generally. And so I'll just write minus I h hat delta t, and I'm going to subdivide this into n, where n is large. I'm going to subdivide it into n short intervals of time evolution. Okay, and so here are those n intervals. Actually, n intervals, n I h hat delta t over n. And okay, so this is n subintervals. So delta t is divided into n subintervals of delta t over n. And then I end up with this n cap of x initial, the I and the f, just mean initial and final. And the next move, why am I breaking it up? Because I introduce a complete set of states, or so-called resolution of the identity in each of these places. So, for example, we know that momentum eigenstates, so let me start here. We know that momentum eigenstates form a complete set. So, if I insert back-to-back momentum eigenstates, and if I sum over the complete basis of momentum eigenstates and insert it there, then that is nothing but the identity. Okay? So I haven't done anything. Now the idea is to keep inserting a complete set of states, but oscillate. So we're going from here to there. We're going to here by inserting the identity and so another resolution of the identity is to insert the complete basis of position eigenstates. Okay? And because I'm going to insert it many times, I'm going to give this particular P here a name, P1. Okay? But then I'm going to insert it in between various others of these factors. And so that'll be P2 and P3 and so on and so on. Okay? Now, I'm going to do the inserting of this and this. So which one do I do? I'm going to start like this. oscillation. Meaning here there'll be an e to the minus I h hat delta t over n factor again. And now the next time I insert something here, I'm going to make it x1, like that, and then there'll be an integral dx1. Okay, and so it keeps going, but always switching between inserting this, then inserting one of these, then inserting the next one. So of course this was x1. The next time I insert anything, it's going to be a complete set called p2. Yeah.
Doesn't this then mean that you have to have some condition like n has to be even or odd or something?
Yeah, we'll spot it in a second. Let's get the idea across, and then at some level we'll clean it up. So let's see.